All right, hello everyone. Welcome to another one of Mr. Martin's physics videos. This is a video for British Columbia Physics 12, looking at charges and Coulomb's laws, or Coulomb's law, singular. So here we're looking at charged particles. We saw how static electricity works and how through conduction or induction things can become charged. Charges can be polarized within an object, and so on and so forth. But what kind of, and we also know that positive and negative charges can attract or repel each other, right? Like charges repel, opposite charges attract. But the next question is then that with what force do they pull or push on each other, right? Because we know that a force is defined as a push or a pull. So how can we calculate, can we measure that force? And Coulomb did a lot of work in this and came up with Coulomb's law and a lot of what we're going to be talking about today. So first, let's fill out some of these notes here. So matter is made of particles which are positively and negatively charged. Okay, the unit of a charge is the Coulomb, after yours truly. All right, abbreviated C. Charges are constant or conserved. I guess that's the better word. Conserved. That means that they cannot be created or destroyed, okay, in the sense that if something has a negative charge, that it maybe have gained electrons from something that now has a positive charge because it lost electrons, okay? It is thought that the total charge of the entire universe is constant and neutral, that there's this balance between positive and negative charges in the universe, which is pretty amazing. Charges are also what we would determine to be quantized, which just means that they occur in finite packages, so they're measurable, and also we kind of group them. The smallest unit of charge is called the elementary charge, which is equal to the charge of one proton or one electron. And just the fact that the charge of one proton is equal but opposite to the one electron is just so fundamental to the universe. Even though it's such a simple thing, it's a big deal, right? And if you were to look at the charge of one elemental charge, right, which is E, all right, it's equal to approximately 1.60 times 10 to the negative 19 coulombs. Okay, another way that you can say this is that there are approximately 6.24 times 10 to the 18 let's say electrons or protons, or these elementary charges, per coulomb. Okay, so if you're looking at, okay, how many electrons are in a coulomb, or how many protons are in a coulomb, then you're looking at this number here. Okay, but if then you're looking at what is the charge of one electron or one proton in coulombs, then you're looking at this here. Okay, Coulomb determined that the force between the two charged objects is proportional to their charges and inversely proportional to the square of the distances, or Fe is equal to K Q1 Q2 over R squared, where Q1 is the first charge in coulombs. The second charge, Q2, is the second charge in coulombs. Radius is distance between charges, and K is Coulomb's constant. Okay. We'll talk about what Coulomb's constant is here. The measurement that our textbook gives us, which is equal to 9 times 10 to the 9, with a bunch of fancy units on it. N times m squared over c squared. Okay, so that's Coulomb's constant, 9 times 10 to the 9. The two important things to notice about this equation, first, that this equation is very similar to our force gravity, right, which is g m1 m2 over r squared. Wowzers. The other thing to notice is that electrostatic forces are much stronger than force gravity, at least in a relative term, okay? And this is most clearly seen in the difference between their constants, right? Where k is 9 times 10 to the 9, and g, was 6.67 times 10 to the negative 11. So you're looking at a difference in order of magnitude of like, 20 zeros here behind the number. That's the amount that they're different. So a very important difference between those forces. There are more important differences between gravitational and electrostatic force. One thing is gravity is always an attractive force. Okay, again, doesn't matter what side of the bed it gets up on, and what its hair looks like. It's always an attractive force. Whereas electrostatic force can attract or repel, okay, based on if the charges are similar or different. Okay, when solving for electrostatic forces, we will not we'll use kind of lightly the positive, negative charges in our equation. Okay, and I'll explain why. Okay, even though the positive and negative charges can tell us whether it's an attractive force or repulsive force, you can usually tell that just by looking at the signs, positive and negative charge, before you plug it into the equation to know what direction. Instead, we're going to determine the direction of the force based on the attraction, repulsion, what we just talked about, and also our free body diagram with our vectors. Okay, so these things will be what will help us keep track of the positives and negatives and the net directions of the forces that we're going to be dealing with. Okay, so let's take a look. Let's do some examples here. So one, let's kind of review what these questions look like in the gravity chapter, where you have this question here. Force gravity, you have two 85 kilogram students are 1 meter apart. What is the gravitational force between them? And so here, my formula, of course, is G is m1 m2 over r squared, which is equal to 6.67 times 10 to the negative 11. 85 and 85 a second time divided by 1 squared. Okay, and that we can just plug into our calculator. 6.67 times 10 to the negative 11 times 85 squared. Because it's 85 times 85, and then divided by 1 squared, which is just what it is. So that gives us, what's our sig figs here? 2 sig figs. 4.8 times 10 to the negative 7 newtons. Okay. If these two students each have a charge of 1 times 10 to the negative 3 coulombs, what is the electrostatic force between them? Okay, so now we're taking these same students, same distance between them, but now instead of looking at the force gravity between them, we're going to look at the static force between them. So Fe is equal to K Q1 Q2 over R squared, K being 9 times 10 to the 9. Q1 is 2.0 times 10 to the negative 3. That's squared because there's two of them, but they're the same charge divided by 1 squared. All right, we plug that into our equation. 9 times 10 to the 9. This is 2 times 10 to the negative 3, and that's squared, and divided by 1 squared, gives us 36,000 newtons, okay? Which kind of gives us an idea of what we're dealing with here when we come to comparing the force electric versus force gravity, and the difference in magnitudes of these forces, right? Even though, they have a mass of 85 kilograms, which is a larger number than the 2 times 10 to the negative 3 coulombs. The force gravity that mass produces, is very small between those two individuals, whereas this charge of, 0.002 coulombs, when you plug that into the equation, you get a much larger force, electric force, attracting these two things, these two students together. Okay, a very significant force. Let's try another question here now, solving for a different part of our equation. So here, 2 point charges of 1.8 times 10 to the negative 6 and 2.4 times 10 to the negative 6 coulombs produce a force of 2.2 times 10 to the negative 3 newtons on each other. How far apart are they? Okay, well, again, I start off with my equation. All right, and then I start plugging in numbers. 2.2 times 10 to the negative 3 is equal to 9 times 10 to the 9. Q1, 1.8 times 10 to the negative 6. It's 1.8 microcoulombs, or times 10 to the negative 6 coulombs. 2.4 times 10 to the negative 6. And then this is all over R squared. So I got to solve for R squared, right? Yeah, so here you can kind of break this down into different sections here. But in the end, you end up with, you can rearrange this equation as this divided by this, right? You're going to get 9 times 10 to the 9, 1.8 times 10 to the negative 6, and 2.4 times 10 to the negative 6, divided by 2.2 times 10 to the negative 3. And then the square root of that, right, because it's R squared, is equal to R. Okay, so then you plug this all into your calculator to get our answer. So, square root, let's get our brackets in our denominator, numerator and denominator separately. 9 times 10 to the 9, 1.8 times 10 to the negative 6, 2.4 times 10 to the negative 6. All right, so that's our numerator divided by 2.2 times 10 to the negative 3. Oops. And I get 4.2 meters. Okay? So again, plug and chug here. We're just dealing with an equation that is very similar to an equation we should be familiar with by now, the universal gravitational, Newton's universal gravitational law. It's gravity. But just changed for static electricity for Coulomb's law here. Okay, now a lot of these questions you're going to have more than one charge. Okay, so this is going to be a very common question here, where you kind of have a tug of war happening between these charges. So here a charge is 1.7 times 10 to the negative 6 coulombs is placed to 2 times 10 to the negative 2 meters, or 2 centimeters, from a charge of 2.5 times 10 to the negative 6 coulombs, and 3.5 times 10 to the negative 2 meters from a charge that is 2 times 10 to the negative 6 coulombs, as shown. Okay, so here it's not really drawn a scale, but we have a distance here of 2 times 10 to the negative 2 meters. Any charge. And then this distance, the total distance is 3.5 times 10 to the negative 2. So this distance is 1.5 times 10 to the negative 2 meters. Okay, so your total distance would be the 3.5 times 10 to the negative 2 meters. Okay, so keep track of that. Don't want to get tripped up there. Okay. What is the net electric force on this charge here? Okay, so the first thing we got to figure out is if these are positive and negative. So here it looks like a charge of positive 1.7 times 10 to the negative 6 coulombs, positive 2.5 times 10 to the negative 6 coulombs, and here this is negative 2 times 10 to the negative 6 coulombs, right? And so the first two charges are positive and positive, and the last one is negative. Okay, so if I'm looking at the charge on this particle here, between the first two particles, I'm going to get a force that's pushing it away, right? Because this one's going to get a force this way between the first two on the left there. They're going to be pushing away from each other, okay? But for the second two, can I use green for this? The second two, because it's a positive and negative charge on the outside, this one's going to be attracted, pulled in by this one, okay? So when you look at the net forces here, you're going to have forces pulling in the opposite directions, okay? And we're not going to use the signs that we get based on the negative charges in our equation. We're actually going to look at a free body diagram to figure out what charges we're dealing with here, okay? So let's start by plugging in some of these numbers. Okay, so force, here we're going to label these A, B, C, just for reference here. So force B on A, and we're looking on the net force on A, okay, on charge. B on A is equal to K Q1 Q2 over R squared, okay, so which is equal to 6.67 times 10. Nope, that's gravitational constant. 9 times 10 to the 9, and then 1.7 times 10 to the negative 6, and then 2.5 times 10 to the negative 6, divided by 2 times 10 to the negative 2 squared. Okay? So let's solve for that force there. Okay, so here I have, just plugging all these numbers in here, 9 times 10 to the 9, and then 1.7 times 10 to the negative 6, then 2.5 times 10 to the negative 6. Okay, and then divided by 2 to the negative 2 squared. All right, and I get a force of 96 newtons. Okay, now what direction is that 96 newtons? Here, because we're looking at the first two charges on the left, that 96 newtons is to the left. Okay, so that's actually, if I'm looking at my free body diagram, if this is my particle A, then now I have a force of 96 newtons to the left, or negative 96 newtons. Now I'm going to use my negative to show the direction of the force, okay? Even though I didn't get a negative in from my equation. Now let's solve for the force on the other one. So force of C on A. Okay, so here I have K again, same equation, Q1, Q2, R squared. Plug in your numbers, 9 times 10 to the 9, 1.7 times 10 to the negative 6, 2. Oh, this one's not 2.5, however. This is 2.0 times 10 to the negative 6. Now here it doesn't matter if I put positive or negative for that 0. I'm going to figure out the direction of that force after I find the magnitude, okay? And they are 3.5 times 10 to the negative 2 meters apart, okay? So again, use my calculator to plug all this stuff in. I could probably reuse much of this equation. All I have to change is that 0. But everything else stays the same, so I end up with this. And then I can probably use this equation. However, now this 2 changes to 3.5. So 3.5. And I'm good to go. Press that, and I get my force of 25 newtons. Okay? And if you look at those two spheres, notice that because they're an attractive force, the force on sphere A is, now that force exists in both places because we know Newton's third law for every action, equal and opposite reaction in terms of the forces here. But we're just interested in this force here. And this force is moving off to the right. So this is going to be a positive force acting on my particle here of 25 newtons. Okay, so when I'm looking for the net force, okay, I'm going to add my two forces, negative 96 newtons plus 25 newtons. Okay, and I'm going to get a net force negative 96 plus 25, get a net force of negative 71 newtons, or 71 newtons to the left. So that means that my particle will move off to the left. Okay? So that's a linear kind of problem. All right? Now let's look at another problem. This is the same kind of question. However, now we have a two-dimensional kind of diagram instead of one-dimensional. All right? So I'm going to change my colors here. We're going to switch over to dark mode. All right? Yeah, what is the net electric force? Yeah, so this would be my answer here. All right. Now let's try this question here. Here we're going to calculate the force on all three of these points, one at a time. Okay, and we're going to have to deal with not just the different forces acting on them, but also the fact that they're acting on different angles. Okay, now we are assuming that the 1.2 centimeters vertically and the 2.3 centimeters horizontally are perpendicular to each other. Okay, and so we'll be able to determine some of the angle stuff with this diagram. Okay, so we can actually, we'll do that in a second. So calculate the net force on A. So here each has, a plus, plus, minus in terms of the magnitude of the charge. And here you have, this should be negative 2.7, the actual charge of spheres A, B, and C in microcoulombs. Okay, remember microcoulombs is, 2.3 times 10 to the negative 6 coulombs. Okay, so you can make those conversions when you enter them into your calculator. All right, so calculate the force on A. So let's solve for A first over here. All right, so first thing we got to do is I'll start with the vertical one, the charge of B on A. So force of B on A. All right, and that's again my equation Q K Q1 Q2 over R squared. Okay, that's the only time I'm going to write it out. And then let's start plugging these values in. So 9 times 10 to the 9. B and A, so here this is 2.3 times 10 to the negative 6 over 3.1 times 10 to the negative 6. And that's all over 1.2 centimeters, so 1.2 times 10 to the negative 2 meters squared. Okay, so let's find that force. Now this is a repulsion force, so when I put my free body diagram, I'm going to represent it as such. So, oops. Let's take a look here. I can reuse a lot of this equation again. It's already written in here. I just got to change some of these values here. So this is 2.3, okay, and this is 3.1. All right, and I'm going to do divided by. I'll try to make all this one equation so that I can reuse what's in my calculator already several times. Squared. Okay, so that should give me my answer. Everything is entered correctly. I press enter, all right, and I get my first force value of, how many sig figs? 2 sig figs here. I'll keep 3 for now. 446 newtons. Okay, so on my free body diagram, I'm looking for the net force on A, right? So my free body diagram is going to include A, okay, and I have this force here that's going upwards of 446 newtons. All right. Now for my next force is looking at the force on from particle C on A. Okay, so for particle C on A, I have to determine a couple things. First of all, I got to determine the distance between A and C. Okay, and I can, because I'm assuming a right angle here, all right, I can find the hypotenuse, okay, and I can also find the angle at which this is going to happen. So let's see here, square root 1.2 squared, 0.2 squared plus 2.3 squared. So I have a distance here of 2.6 centimeters. All right. And an angle in degree of 0.2 divided by 2.3 of 27.6 degrees. 27.6 degrees. All right. So that's going to be helpful once I start, drawing tip-to-tail diagram here to find the net direction that I'm going to be. You're going to see these are big questions. Just to do A is going to take a long time. I might do B and then leave C for you guys to try. Okay, but this is from your practice problems in your textbook as well. So different numbers, but same kind of question. All right, so first I just need to find the magnitude of the force. So it is 9 times 10 to the 9. Charge A is still that 2.3 times 10 to the 6, okay? Charge C is negative, but I'll enter it as a positive just because it doesn't matter the positive or negative. It just matters the direction I'm going to draw it on my vector, my free body diagram here. Okay, that's what's going to help me determine these, the direction of these forces. So times 10 to the negative 6. And then the distance between the two we determined to be 2.6 times 10 to the 6, negative 6. Times 10 to the negative 2. Times 10 to the negative 2. Okay? And then that's squared. All right, so I'm going to enter that into my calculator. Did I make that mistake up here? No, I didn't. Okay, so all the numbers at first, 2.3. I'm going to change the 3.1 to 2.7. All right, and the distance is not 1.2. The distance is 2.6. But otherwise, everything else is constant. I press enter, okay, and I get a force of 82.7 newtons. 82.7 newtons. Okay? Now here, because it's an attraction force on particle A, that vector is drawn like this. Okay? This is 82.7 newtons. Oops. At an angle of 27.6 degrees. Okay? You can kind of see that angle and, this angle should be the same. All right? So that is the direction of that force, because I know that C is attracting particle A towards it. Okay, but B is pushing particle A away from it. So that's how we get the direction of those vectors. All right. So now we need the net force. Okay, so we got to draw these vectors tip to tail. So I take my first vector, 446 newtons. I take my second vector, so I draw a horizontal, and that's going to be 27.6 degrees down from the horizontal at a magnitude of 82.7 newtons. Okay, and I want to solve, okay, what is the resultant? What is this? Because this is my net force. Okay, so I know some of the values in here, the degrees. Actually, I just know one. I just know this one. Let me redraw my lines here. Okay, that's like that. The magnitude of this line is 82.7 newtons. Yeah. But the degrees here, because this angle is 90, okay, if I do 90 minus 27.6, I get the angle here of 62.4 degrees. Okay? So I can use the cosine law to solve for the magnitude of that line, and then I can solve for the angle of that line again. Okay, so this is all in one question. So cosine law, c squared is equal to a squared plus b squared minus 2ab cos c. All right, so the c squared is what I'm solving for, so it's going to be c is equal to square root, what's my a, doesn't matter, 446 squared plus 82.7 squared minus 2, 446, 82.7 cos 62.4 degrees, all under my square root symbol, and that'll be the magnitude of my net force. So let's get to work. 446 squared plus 82.7 squared minus 2, let's say 2, 446, 82.7 cos 62.4. Press enter, and I get a magnitude of 414 newtons. Okay, and then the direction here, this is equal to 414 newtons. Here you can use sine law to solve for, and I want the direction here. Or maybe this angle here, but solve for this angle and then use the 90-degree kind of rule to solve for the angle from the horizontal. Okay, so this is the angle I want you guys to solve for here. So just to kind of finish off this question, I'm dealing with sine A over A is equal to sine B over B, right? So this would be sine 62.4 is to 414 what sine B is to, what's the side opposite to the angle I want? 82.7. 82.7 newtons. Okay. So it's 82.7 sine 62.4 divided by 414, and then inverse sine or arc sine that, and I get an angle of 10 degrees. Okay, so if this angle here is 10 degrees, okay, then this angle here is 80 degrees. So my final answer for A would be 414 newtons, 80 degrees above horizontal. That's a long question. Okay, but that's what you're looking at. Okay, let's do B. Okay, and then I'll leave you guys to try C. Okay, and then we can discuss it together when we meet up next. Okay, so B should be more straightforward here because B is in the corner, so it's going to be repulsed downwards by the A particle and pulled to the right by the C particle. Okay, so here, force A on B, of course, is equal to force B on A. So I already know the magnitude is 446 newtons. Okay, because I determined that right up here. Okay, so I don't have to recalculate that. So then my free body diagram, my B particle, and then this force is now, instead of 446 up, because I'm talking about the B particle, that B particle is being pushed down by 446 newtons. It's being pushed down by 446 newtons. Okay? But now I still have to solve for the force C, particle C on B, okay, which I have not done yet. And so that's going to be 9 times 10 to the 9. The charges are teeny tiny way up there. B on C, so 3.1 times 10 to the negative 6. And then 2.7 times 10 to the negative 6. Again, I don't have to worry about the negative. I'll figure out what the negative is when I put it into my free body diagram. And then they are how far apart? 2.3 times 10 to the negative 2 meters apart. And I have to square that. So plug that into my calculator. I already have most of that already in here. I just have to tweak it. So I have 9, 2.7's there. I need to change this to 3.1. All right, good. And the distance between is 2.3. Awesome. Press enter. And I get 142 newtons. Okay? And again, because I know that B is being attracted to C, pulled to the right, okay, that gives me the direction of this vector. 142 newtons to the right. Okay? Now these ones are a lot easier to put tip to tail just because they're perpendicular to each other. So this is going to be a little bit easier. I have this force here of 142 newtons. And then I have this force here, not to scale, of 446 newtons. Okay, and I want to solve, get out of here. I want to solve for the resultant. Okay, this is what I want here, knowing that these are perpendicular. So a lot of this math is, a much easier trig from before. So here I just need Pythagorean theorem, 446 squared plus 142 squared. That's going to give me the magnitude of my force net, 468 newtons. Okay, and then here I can say below the horizontal by solving for this angle here. So then I can just use tan for that. So 446 divided by 142, which would give me 72 degrees below the horizontal. So your final answer here for force net on B would be 468 newtons, 72 degrees below horizontal. And when I say horizontal, I'm always assuming the positive x-axis. Okay, so just so that's clear. So that's A and B. Go ahead and give C a try. Try to get it and ask me about it next class. Okay, but that's essentially what your that second practice problem in your work textbooks looks like. Okay, these are significant questions, right? So I want you guys to get some reps under your belt for these questions.